Yesterday, we established that there is a force of gravity acting between any two objects with mass. Now, that force of gravity depends upon the values of the mass, the magnitude of the mass. So you know that the force of gravity between two small things is going to be a pretty small force, right? If it's dependent upon the masses, small masses give you a small force. But if it's a big mass or big masses, then it's going to be a big force. That force of gravity is the force that causes an apple to fall towards the ground, but it's also the force that causes the Earth to orbit around the sun. It can be a small force, it can be a big force, depending upon the masses. What else is it dependent upon besides the masses, the product of the masses? Bigger the masses, bigger the force. Julia, what's the other thing? Yeah, the separation distance. Now we call that R, but it's not radius necessarily, it's the separation distance. And in fact, it's actually R squared, and it appears on the bottom. It appears on the bottom because the bigger the separation distance, the smaller the force. As M goes up, F goes up. But as R goes up, F goes down. Now, it's not exactly equal to M1, M2 over R squared, but it's close. We put that little fudge factor in front of it, that constant in front of it, G, the gravitational constant. And the value of that's on your data sheet, right? It's 6.67 times 10 to the minus 11 Newton meter squared per kilogram squared. When we find this force of gravity between any two objects with mass, understand that that force of gravity is the force acting on both of the objects. So if we have object A and we have object B, and we want to find the force of gravity between them, then we're going to use that equation. If we want to find the force of gravity acting on object A, which is toward the right because it's attracted towards B, then we'd use that equation. If we want to find the force of gravity acting on B, it would be to the left, and we'd use that equation. It's towards A, and we would use that equation. If object A applies a force on object B applies an equal and opposite force on object A. When I drop this pen towards the ground, the Earth applies the force of gravity acting on the pen, right? Does the pen apply a force acting on the Earth? Sure it does. Is it equal? Absolutely it is. Okay, if Earth applies force on pen, pen applies equal and opposite force on Earth. Why is it then that the pen falls toward the Earth, but the Earth doesn't rise towards the pen? Shouldn't the Earth, I say rise toward the pen, okay, it would be like falling, right? Gravity causes things to fall. Shouldn't the Earth fall towards the pen? It does. It does. But if you have a force of 10 newtons acting on the pen, 10 newtons is enough to notice an effect on the pen. That same force is applied back on the Earth, and it does pull the Earth up ever so slightly. But are you ever going to notice the effect on the Earth when a force of 10 newtons is applied on it? No. Like it would be immeasurable. It would be impossible to measure that value of the acceleration because it would be so ridiculously small. All right. Yesterday, we went a little step further and we learned to analyze a situation where we had 3 objects in a row. And that's what your homework question was on, right? 3 objects in a row. Let's say we had object A, B, and C, and we wanted to find the net force acting on object B. The force of object A on B would be which way? A attracts B, right? A applies a force on B. Which way is the force on B as a result of A? Okay, left fist is A, right fist is B. They get pulled together, right? Now A gets pulled to the right. I don't care. I don't care what happens to A because the force that I'm trying to find is the force on B. It gets pulled to the left. Okay, now what about B and C? Well, they get pulled towards each other as well. C gets pulled to the left, don't really care. B gets pulled to the right. That's what I care about. Now, we want to analyze this. We're going to find both of these forces, the force of A on B, that would be my fab force. Okay, and the force of C on B, that would be my force. We add those together. What do we got to be careful of when we add them together? The direction, right? FAB is going to be a negative value. FCB is going to be a positive value. Listen, once you get these values here, it's just a question you did the last unit, right? The net force is the sum of the forces. Make sure you make the signs right. Okay, let's take a look at the homework that you had here now. Question number 1 was the one that I said, you got to do this. And then question number 2 was that challenge question that I threw out at you here. Number 1 says, during a solar eclipse, the Earth, the Moon, and the Sun are aligned in the same plane as shown in the diagram below. Calculate the net gravitational force exerted by both the moon and the sun on the Earth. Well, let's look at the moon on the Earth first. The force of the moon on the Earth is which way? Let's forget about the sun. Pretend it doesn't exist for a second. Do the moon and the Earth exert a force of gravity on each other? Yeah, they do. Look, the Earth gets pulled to the right, the moon gets pulled to the left, right? We don't care about the force on the moon. That's not the question. The question is what happens to the Earth. So let's draw the force of the moon on the Earth to the right. The force of the Earth on the moon is to the left. We don't care. Unless we were trying to find the net force on the moon, then we would care. All right, what about the sun? Now let's pretend the moon doesn't exist. Do the sun and the Earth attract or repel each other? They attract each other, right? So that means the sun will be pulled to the left. We don't really care about that one. The Earth will be pulled to the right. That's the one we care about. I'm going to say the force of the sun on the Earth is to the right. Now let's get the values of both of those forces. The good news is in the example question, we already did that. The force of the moon on the Earth in the example question that we did yesterday was what? GM1M2 over R squared, right? GM1M2 over R squared. This mass over this distance squared. What was its value? 1.98 times 10 to the 20 newtons. Good. And what about the force of the sun on the Earth? Okay, that would be, we calculated that yesterday for the example question as well. That was a bigger force, wasn't it? Something times 10 to the 22. Let's go a couple more decimal places for that one. Times 10 to the 22. All right, now we say F net is equal to the sum of the forces, like we've done a million times over the last couple months. The net force is equal to ME, force of ME, force SE. ME is negative 1.98. No, sorry, it isn't, is it? They're both positive, aren't they? In the example we did yesterday, one of them was negative, right? Because one of them was to the left. But they're both positive this time. We're going to say 1.98 times 10 to the 20 newtons plus 3.5218 times 10 to the 22 newtons. And what do we get? I think yesterday was when the Earth was between the moon and the sun. I think it was 3.50, wasn't it? 3.54 times 10 to the 22 newtons. Make sense? I don't know for sure. I've never actually seen this or heard this, but we talked a little bit about tides yesterday, right? It would seem logical to me that during a solar eclipse, tides might be stronger, like tides might be higher. Okay, if that's in fact the case, why would it be the case? Yep. Yeah, because the force of the moon and the sun are in the same direction. If you get the moon on the other side of the Earth, the force was 3.50 times 10 to the 22 newtons. If you have them on the same side, like right here, the force is 3.54 times 10 to the 22 newtons. So it would seem to me, seem pretty logical that you'd end up getting higher tides as a result of that. Good. How many people did number two? How many people tried number two? Okay, how many people got number two? Look at that. The people that tried number two got number two. This is a question where I'm confident that if you tried it, you had a good chance of getting it, even though we've never done a question like this. Now, this is really a combination of stuff that we've done through this year, stuff that we've done over the last couple of days with stuff that we've done way, way earlier in the year. It says, during the first quarter phase of the moon, Earth, the moon, and the sun are positioned as shown in the diagram here. Calculate the net gravitational force exerted by both the moon and the sun on the Earth. Well, the moon causes the Earth to be pulled up this way. The force of the moon on the Earth. The force of the sun on the Earth is this way. We know the values of the moon on the Earth, right? We just used them. The force of the moon on the Earth was 1.98 times 10 to the 20. And the distances are the same. So the value of that force is going to be the same. If you don't remember how to get that, remember it's just G m1 m2 over r squared. Okay, get the value of that force of the moon on the Earth. And then get the value of the force of the sun on the Earth, which we already have from the previous question, 3.5218 times 10 to the 22 newtons. Well, then what do we got to do? We know we got to add them up, right? If you want to find the net force, net means sum. So we got to add them up. But how do we add these up? How do we add these up, Julia? Yeah, look, we've got two forces that are, well, it looks like they both should be positive, right? Because one's to the right, one's up. So shouldn't we just say 3.52 plus 1.98, same as we did in the last one? No, of course not. Why can't we? Julia, why do we have to draw the vector diagram there? Yeah, they're not both in one dimension, right? They're in two different dimensions. We can't just, we got to add them, but we can't add them up the normal way. We got to draw the vector diagram. Here's 3.5218 times 10 to the 22, and here's 1.98 times 10 to the 20. And we do this, we find the hypotenuse, that would be the value of r, and I think when we do that we get 3.52. And we got to find the value of theta as well. I can see the answer there is 0.3. How would I predict the answer is going to be not 0.3, but really, really small? How would I know when I look at this the answer is going to be small? Yep, Holly? Yeah, like you look at the x value, 3.5, the y value, 1.98. On the surface, they look like not that far off, right? But when you look at the exponent, 10 to the 22, 10 to the 20, this one's like 100 times bigger than this one. So you are going to get a really small angle. Yeah, I wouldn't have had any idea exactly what it was going to be, but I would have predicted that it was going to be really small. 1.98 times 10 to the 20 divided by 3.5218 times 10 to the 22. And I assume when you do that, you get 0.3 degrees. They made a little mistake, though, with sig figs, right? Should be two significant figures, right? What does it work out to be the two digits? 0.3. The leading zero is not significant, right? That doesn't count. Is it 3.0? 0.323? Oh, you're saying shouldn't it be three significant digits? Yeah, it should actually. Yeah. 0.323 degrees. Remember that first zero doesn't count, right? Good there? How many people think if they had tried that they could have got that? Then you should have tried it. Then you should have tried it. I know you could have gotten it. I know most of you could have gotten that. Okay, challenge yourself a little bit. If it's the kind of thing where I say, hey, try this as a challenge question, and it's going to take you 2 hours. Well, okay, I get that you don't want to try it, right? But it's going to take you 5 minutes. Give it a try. See what you can do. All right, I want to spend a few minutes right now, just a few minutes, talking about where the value of G came from. And then we're going to move on to what's going to help you with question number 3 on your assignment. It's called gravitational fields. The experiment that was performed in order to determine the value of G wasn't performed by Newton. Newton came up with the law. Newton came up with the relationship. He was the guy that said there's a force of gravity acting between these two objects with mass, but he didn't know what the value of G was. So Cavendish devises this brilliant experiment to determine the value of G. And I'm going to simplify it a little bit, but it's going to give you the gist of what was going on there. We have a ceiling, or the top of a box. Attached to that is a string. Attached to that string would be a rod. And attached to either end of that rod would be a mass. We're going to call one of them mass 1, and the other one we're not even going to name. It doesn't really matter. We got to put it there in order for this rod to not tip over. We got to have it balanced. But other than that, it doesn't really matter what it is. So we've got a name on one of them, we'll call it mass 1. Well, there's got to be another mass involved here, mass 2, but the one on the right side is not mass 2. My fist is going to represent mass 2, or I'll draw it on the page, actually. Mass 2 is coming nearby mass 1. As I bring mass 2 nearby mass 1, there will be an ever so slight force of attraction between mass 2 and mass 1, right? A really, really small force of attraction between the two of them. Now, we can measure a number of variables here. Okay, we can measure the mass of object number 1. Okay, that's easy, right? Measure the mass of object number 1. Okay, that's the mass that's right there. We can also measure the mass of object number 2. That would be my fist, or the object that I have drawn on the page right there. Okay, easy enough. I can measure the value of R. How far apart are the two masses? Okay, that's easy to measure. Use a ruler. I can measure the value of the force as well. Now, this is a little bit trickier. We call it the torsion balance experiment. Anybody know what torsion means, by the way? Torsion, twisting. You ever go on a swing set as a kid and start twisting the swing set around as far as you can, and then let it go so that you can start swinging around as fast as you can? Everybody's done that, right? Intuitively, you know the more you twist it, the harder it becomes to twist, the bigger the force required to twist it. You could do experiments to figure out, to measure the value of the forces, the value of the force required to twist it a quarter of a turn, a half a turn, 3/4 of a turn. Turn it twice, all the way around 2 times or 4 times or whatever the case may be. You could create a little table that said, oh, if I twist it 37 degrees, then it was this much force that was required to twist it that much. That's what Cavendish would have done. Cavendish would have known the value of the force required to twist this string, right? When I bring the mass nearby, mass 2 nearby mass number 1, mass 1 is attracted towards number 2, and therefore the string that the rod is attached to will twist. If Cavendish knows how much force is required to twist it a certain amount, then he can measure the force when I bring mass 2 nearby mass 1. Look, bring it nearby mass 1, it twists. Oh, let's measure the amount of twisting, and then let's determine the force from that. The Cavendish torsion balance experiment, or the Cavendish twisting balance experiment. We measure the force by the amount of twisting of the string. Well, now we've got M1, M2, R, and F. The only thing we don't have is G. So in essence, we're going to take the law that Newton already had come up with, rearrange it to solve for the value of the constant that Newton didn't know, and calculate the value of G. Well, and behold, it works out to be 6.67 times 10 to the minus 11. Does that make sense? We're going to talk about one next year called the Coulomb torsion balance experiment. It's almost identical, except we're not using masses, we're using electric charges. Next year when we go through that, I want you to remember this. Okay, think back to this, because next year that's going to make a whole lot more sense if you remember this. Bring two masses nearby one another, measure the value of both masses, measure the distance that separates them, and measure the value of the force between them by how much the string twists. Then determine the value of G, 6.67 times 10 to the minus 11. I'm going to give you a few questions to work on here. I'm going to give you a few minutes to work on them in class, about 5-7 minutes here. See what you can do with page 215, number 1 and 2, and then questions 4 to 7. And then we'll move on to our new topic that's going to help you with question number 3 on your assignment.